Good morning, our students, and welcome to this as discussion. Today is somehow a continuation of the class that we had yesterday. Yesterday, we discussed an aspect of a time series called backward shift operator, or what we call lag operator. And the essence of lag operator is that when the time series model continues to become complex, the operator actually assists us to write these models in a very compact word form. It both helps in writing the models in a compact form and equally helps in manipulating or calculating these models. And again, today we want to look at another aspect of a time series equally called differencing. And there is a link between the differencing and then the backward shift operator, which we are going to see on the course of this discussion. But first of all, we want to make our audience to understand the essence of differencing in time series data or in time series. The models we have in time series have different assumptions that will be met before any result coming out of these models can be adequate. And one of these assumptions is the stationarity of the data set or the stationarity of the series. And when we say that a data is stationary, there are three things we are looking out to see in that data. Number one, that data is going to have what we call a constant mean. It is going to have what we call constant variance, and it is going to have what we call constant covariance over time. I say it is going to have what we call the constant mean, have what we call constant mean, a constant mean. It is going to have what we call the constant variance, and then it is equally going to have what we call constant autocovariance, autocovariance over time, over time. So the moment we have a data set and then we check out for these three attributes and they are met in a data set, we can go ahead to say that that data set is stationary. However, if any of them is violated, of course, we begin to look at that data as something that is not stationary. However, it is important to note that in real life situations, our data sets are hardly stationary. And because they are hardly stationary now, you find it difficult now to apply any of these time series models. So the primary thing you are going to do there is to first of all see if you can convert the data set which you have at hand, which is not stationary, into being stationary data sets. And one of the primary method or approach of converting a data set that is not stationary into being stationary data is what we call differencing. What we call what? Differencing. We call it what? Differencing. So, in the differencing, what does this differencing do in our data set to make it now to become stationary? It helps us to remove what we call the linear trend. It equally helps us to remove what we call the seasonal trend. And then helps us equally to remove what we call the structural component of that time series that makes it now to be non-stationary. That is actually what this differencing does. What is the symbol of this differencing and how is it expressed? When you talk about talk about the differencing. The symbol of this differencing is given as this. So anywhere you see this in time series, it is making reference to what we call differencing. How is this symbol differencing expressed? It is expressed as 1 minus what? B. That is how to express this symbol. Where this B here stands for what we call the backward shift operator or the lag operator. What we call the backward shift operator, or we can call it the lag operator. Okay? So for the fact that you have seen the symbol of differencing, and then you have seen how it is expressed, and you have known the reason of differencing, that our series is not stationary. Let us consider a time series represented by y of t. A series that is represented by what? By y of t. Let us have information that this y of t is not a stationary series. And we want to apply differencing on it now to make it now to be stationary. We are first of all going to look at what we call the first differencing, look at what we call the second differencing. In the first differencing, the target is to remove what we call the linear trend. When we talk about the second differencing now, we are suspecting what we call a quadratic trend or a strong trend in it that might not easily be removed by just the first differencing. So when we talk about first differencing, this symbol will be written like this. The first differencing, first D. I'm referring this D to be differencing. The first differencing, this symbol will be written as this, raised to power 1. And then the essence is to different this data y of t. And we have seen that this symbol here is expressed this way. So this thing implies that this is 1 minus what? Minus b, all raised to power 1 y of what? Of t. Which of course now can be expressed this way. When anything is raised to power 1, it is that it is itself. So we use this y of t to open a bracket, and what we are going to have here becomes what? Y of t times 1 will give us what? Y of t. This sign is minus. This operator here, b, will multiply y of t, and we have b y of what? Of t. Yesterday we explained that the function of the backward shift operator is to shift the time index of a time series now one step backward. So this thing becomes what? Y of what? Of t minus what? Y of t minus 1. So by having this, it implies that you have differenced this your original series y of t by once. You have differenced it once. And then what you have here is y of t minus y of t minus 1. So by differencing, okay, what you are simply doing is to subtract the value of the series in the past from the value of the series in the current time. That is what we are doing. So while the backward shift operator is simply converting the current time series now into its previous value, the differencing is subtracting its previous value from the current observation. Yesterday we said that whenever we have b of y of what? Of t, that the answer becomes what? Y of t minus 1. This is what we call a backward shift operator. It has operated on this series y of t. The answer is y of t minus 1, which is the value of the series now one step backward. But when you are talking about differencing, what you are doing now is the value of the current series minus the value in its previous one step backward, or in its one step backward. So that is the little difference between what is called the backward shift operator and then the differencing. This thing we looked at here is called the first differencing. Let us look at the second difference. If you talk about the second differencing, what you are now going to have here becomes, you have this symbol. This is second. This second differencing. Second what? D. Permit me to write as second differencing. Second D. The symbol, of course, will be written as this, which is going to be raised to power 2. And our essence is to difference this y of t what? Twice. You know quite alright that we can break this symbol into two, and this thing becomes what? We have this symbol, we open a bracket. We equally have that symbol again, we close it. We have y of what? Of t. It can be broken down that way. And we know quite alright that this one alone that is here, this one, we can put it this way. Or let me put it this way. Then we have what? Y of t. This symbol raised to power 2 multiplied by y of t can be broken down this way. And this thing becomes is equals. I have that symbol outside. I will open a bracket. This my symbol y of t, that is first difference of this series y of t, we earlier got it to be this. So it means that what I have here becomes y of what? Of t minus what? Y of t minus 1. I close it. This is equals. And we have already told ourselves here that by differencing, it is always the value of the series at a particular time minus the value of the series at its previous time. So we must first of all write the value of the series at that particular time. This is the value of this series at this particular time. Okay? So I'll write it the way it is, which is y of t minus what? Y of t minus 1. I will open and close. By the idea of differencing, I have to say minus. I now begin now to talk about now the value of the series now one step back. I will apply the one step back here. I will equally apply the one step back here. So applying the one step back here, what I'm going to have here becomes y of t minus 1 minus. I will equally apply it here, which is y of t minus what? 2. Close it. By having this, what you have succeeded doing is that you have differenced this original series y of t twice. And your data set or series has become y of t minus y of t minus 1 minus y of t minus 1 minus y of t minus 2. That is what you have there. So if you talk about what we call the dth order differencing, this is the first order differencing, second order difference. You can say dth, you can say the mth order differencing. What you are going to have that place becomes the dth order now becomes dth difference now is now going to be written as what? This raised to power d y of what? T. And you know quite alright that this your symbol of differencing is expressed this way. So it is now going to be this equals 1 minus what? B all raised to power what? D y of what? Of t. And by this, you have different this original series y of t by into d different time. That is what we call differencing in time series. How are we going to introduce this differencing now? Or how are we going to use the idea of difference now to write the different kind of ARIMA models that we have? Which is, of course, the essence of even this class. So let me quickly clean here now and show us how we can then apply this difference now in different kind of ARIMA models that we have. You know that when we talk about ARIMA, we are talking about an AMA process that is not stationary, which we have decided now to make stationary. So when we talk about something like this, if we talk about, let me say, we talk about AMA 1, 1. If you talk about AMA 1, 1, you are talking about a series that combines MAR of order 1 and MA of order 1. And you can write such a series this way. You can say that such series is what? Y of t is given as, you have what we call phi 1 y of t minus 1, then plus, you have what? A of what? T, then plus, you have theta 1 a of t minus 1. This is how to write AMA 1, 1. Okay? So if you write this AMA 1, 1, first of all, let us use now the backward operator to bring them together. This is going to be, we bring this one over here, and what we have here becomes y of t minus phi 1 y of t minus 1. This is giving us what? A of t plus theta 1 a of t minus 1. So when we apply the backward shift operator here, what we are going to have here becomes what? Y of t minus. We have phi 1 b y of what? T. It is no longer t minus 1 because of the place of this b. Because if I apply this b on this t, it becomes t minus 1. This becomes, I have what? A of t plus theta 1 b a of t. Because of the place of this b, it is no longer t minus 1, it becomes t. Because once I apply this b to this t, it becomes t minus 1. Because I have a of y of t here, y of t, I'll factor it out. And what I have here becomes 1 minus what? We have phi 1, then b, close it, y of what? T. This is equals. A of t is here, a of t here, I'll equally factor it. 1 plus. We have theta 1 of b, we have what? A of what? Of t. And I have now used a backward shift operator now to write this AMA 1, 1. Let us say that we have information that this AMA 1, 1 is not stationary, that we want to difference it. Remember that when you are differencing the AMA process, where your interest should be is on the AR model, because you cannot talk about stationarity when you are discussing MA. Instead, we are talking about what is called invertibility condition. So all MA under normal circumstances are stationary models. You understand? So where you now talk about applying the differencing is on the MAR component of what? Of the series. So what we are going to do now is look at where the AR component is. Look at where the MA component is. AR component is here because it depends on what? On the previous value of the series. Then MA component here because it depends on the previous value of the error term. That's why you saw here a of t minus 1, and we are seeing here y of t minus 1. So what I'm going to do now here is to do something like this. I will now come and do something like this. 1 minus. We have phi 1 of what? B, close it. We want to difference this thing only once. So, and when we difference it only once, permit me to write it this. When we difference it only once, what we are going to have is what? Arima 1, 1, 1. This I here is talking about the order of differencing, or what we call the differencing symbol integrated. And we are writing it here to, last time we had what? 1, 1. 1 here is AR, 1 here is MA. This one at the center here is talking about the order of the differences. So I have only differenced what? Once. So I am now going to write AMA using this process. So this becomes now 1 minus phi 1 of B, then you now stop. Then for you now to introduce this differencing, the symbol of difference like we said before is this. And we are differencing once. Y of what? T. This is given as 1 plus what? We have theta 1 of B, A of what? Of T. And we know the symbol of this differencing. So we can say 1 minus phi 1 of B, then we open a bracket and say 1 minus what? B, Y of what? T. This is given as a 1 plus theta 1 of B, then A of what? Of T. So anytime you see this, by yourself, you can interpret this thing to be Arima 1, 1, 1. Because this place is talking about the order of differencing or the differential component. This one is talking about the AR component, while this one is talking about the MA component. And yesterday we said, let this 1 minus phi 1b be phi b. So I can equally write this into b phi b into 1 minus what? B y of t is equals to theta what? B a of t. You can equally write it this way. So any of these things you see is talking about AMA 1y. So how can we then write what? AMA 110, for instance. How can we write AMA 011? Let us first of all start from AREMA 011. If we talk about AREMA 011, AREMA 0, or let me say 110. What 110 means that it has AR component. It was different, but it doesn't have MA component. So to write the AMA, this AMA first, leaving the order of difference in first, we are going to write it like this, that this is y of t is given as phi 1 y of t minus 1, okay, plus what? A of what? T. By the implication, this is 0. It doesn't have the MA component. Then you first of all now use the backward shift operator to bring it close, which is y of t minus phi 1 y of t minus 1. This is equals to what? A of t. So you now by bringing in the shift operator, y of what? T minus phi 1 b y of t, this is equals to what? A of t. Then you now factor and you have 1 minus what? Phi 1 of b y of what? T, this is equals to what? A of t. You now want to go and apply the difference now. So applying the difference now, what you are going to have here becomes 1 minus phi 1 of what? B. You open a bracket, that your symbol this, which is now 1 minus. You have what is called what? The B, close the bracket. You have y of what? T. This equals to what? A of t. Which you can as well write what? Phi of B, 1 minus what? B of y of t. This is equals to what? A of t. So if they ask you now to write the AREMA 11 model, you either write it this way or you write it this way. AREMA 11 model. You either write it this way or you write it this way. Okay? So how do we now write something like a AREMA 121 or even AREMA 120? How are we going to write it? So it means that we are going to use this approach. Permit me to clean here. If we are to write that 20, it means that we are going to have something like this. So this is AREMA. AREMA what? 1, 2, 0. So in that case, what we are going to have, or we can even say 1, 2, 1. First of all, write your AMA 1, 1 before we talk about order of difference. And then for us to write AMA 1, 1, it is what? Y of t is equals to phi 1 y of t minus 1 plus a of t plus theta 1 a of t minus 1. Applying all we have explained earlier, we are going to arrive at 1 minus phi 1 of b y of t. This is equals 1 plus theta 1 of b, then a of t. This is now how to write it now using the backward shift operator. Then we now talk about this differencing. So which is now second order differencing. And it becomes 1 minus phi 1 of b. Then I will now apply that differencing, which is this symbol, by 2. Then we now have what? Y of t, then which becomes what? 1 plus what? Theta 1 of b, a of t. And we know what this symbol is, that this symbol can be written this way, that this becomes 1 minus what? Phi 1 of b. Then we now write only 1 and open a bracket and write only 1 again, y of t, close it. This becomes 1 plus theta 1 b A of t. Then, and we know what this one that is inside the bracket is, that it is given as 1 minus phi 1 of what? B. Anyway, you can even write it like this and leave it. This one is just because we are trying to expand it. So you now have this thing this way, this symbol once. Here you have y of t minus y of t minus 1. Close it. This equals 1 plus theta 1 of b. You have a of what? Of t. If you apply this one on this one, you end up going to have something like this. 1 minus what? Phi 1 of what? B. You open. Then you now do something, you open again. And then you have, use this kind of brackets. Then you have y of t minus 1, y of t minus 1, close it, minus. You open a bracket again, y of t minus 1 minus y of t minus 2, you close it. You now close with this bracket, you write y. Then there is no need of y of t because you have expanded everything. Then you now close it and say this equals whatever value that you have here. And by that, you have written your AREMA 121. So this is how to apply backward shift operator on time series, how to apply both backward shift operator and then the order of difference in our time series models. I think we have known how to handle the backward shift operator and how to deal with differencing. The next we are going to have is to begin to consider these complex models beginning from AMA models. Thank you very much for your audience for today, and stay connected as we still continue to bring classes that is worth changing your understanding of statistics for good.